Hey guys, welcome back to part two. We're going to go over some example problems and look at some of the gas laws that are ahead of us that help to kind of show what pneumatics do and how when they are designed that you have to account for different variables. All right, so let's get started. So the perfect gas laws describe the behavior of pneumatic systems, and those three laws are going to be Boyle's law, Charles' law, and Gay-Lussac's law. So what is true is that the volume of a gas at a constant temperature varies inversely with the pressure exerted. And when we say inversely, that means as one goes up, the other goes down, or as one goes down, the other goes up. And this should make sense, right? So as we decrease the volume, the pressure increases, right? And hopefully we've seen this before when you try to push on things. That should make sense, right? So as we're increasing pressure, the volume decreases, right? That only seems natural. So let's see how this is applied. And this is the problem, the formula, that you're going to be using. And that's that pressure 1 times volume 1, that might be the start pressure, is equal to pressure 2 times volume 2. But we have to be careful of a few things, and we'll talk about those things. Okay, of course, we know V is the symbol for volume, and example units are going to be inches cubed. That's what we can use. We can always use centimeters cubed. Those are our typical units. All right, so an example here. A cylinder is filled with 40 cubic inches of air at pressure 60 psi. The cylinder is compressed to 10 cubic inches. What is the resulting absolute pressure? And if we go back to our conversation about absolute pressure is gauge pressure, right, plus atmospheric pressure. So that's the one thing that most students kind of miss, and so we have to be careful. So again, we're going ahead and we're taking the cylinder and pressing it from 40 cubic inches into 10. So let's look at our variables here. P1, which is pressure 1, is 60 pounds per square inch, and volume 1 is 40 cubic inches, volume 2 is 10 cubic inches, and we need to find pressure 2. But before we do that, we're going to need to convert P1 to absolute pressure. And we assume that everything we're at sea level. So that means that we're going to take 60 pounds per square inch and add 14.7 that is the atmospheric pressure at that level to get 74.7, which is our absolute pressure in the system. And we must use this or it's not going to turn out. I can do an explanation later, but you can't just add or subtract 14.7 at the end. It won't work for you. So make sure that you do this. Okay. And again, there's our formula. And so essentially we just substitute the variables in, and it looks like in the end we're just going to go ahead and divide by 10. They do a little bit of rounding here, so just be aware. And they get around essentially 300 pounds per square inch. I know that your answer is going to vary. They are doing some rounding here in the end, so don't worry about that too much. Okay, Charles' law says the following, that a volume of a gas increases or decreases as the temperature increases or decreases. And this is more of a direct variation instead of an indirect. So as temperature increases, the volume increases, right? Because those molecules in there, the gas molecules, want to move around. They want more space to move around in, so they kind of drive it up, right? As I increase the temperature, the gas wants more space to move in, so it kind of drives the volume up. That's how we can think about that. And the formula here is V1 over T1 equals V2 over T2. Now, if that really wouldn't matter if you flipped it over and put T1 over V1 and T2 over V2. That wouldn't matter too much. Just keep that in mind as you do these problems. So if you get stuck on, oh my God, which one is the numerator, which one's the denominator, just put the one that you want to solve for on top. And that can make more sense a little later, but don't get caught up on that. At any rate, an expandable container is filled with 28 cubic inches of air, which is of course a volume, and is sitting in an ice water that is 32 degrees Fahrenheit, which means that would be T1. The container is removed from the icy water and is heated to 200 degrees Fahrenheit. What is the resulting volume? So we do want to use the formula, but just like Boyle's law, we have to be careful, and we're going to have to convert our temperature into Rankine. And so how do we do that? There's our variables, excuse me, and now we're doing our conversion. So again, we're going to convert T1, which is 32 degrees, into Rankine. That's what we have to use in this formula. That is how these variables work. So we're just adding 460 degrees, and now that gives us 492 Rankine, as well as 460 to 200, which gives us 660. And now let's plug it in our formula, that ratio. So as we plug it in, V1 over T1 equals V2 over T2. It's going to look something like this. And we're going to go ahead and we would multiply, of course, by 660 on both sides. And that would give you V2 being 38 cubic inches in the end. Okay, Gay-Lussac's law says that absolute pressure of a gas increases or decreases as the temperature increases or decreases, provided the amount of gas in the volume remain constant. So to kind of show you a picture of this, right, again, as I heat everything up, right, what's going to happen? We're increasing the pressure, right? So no, T1 and T2 again revert to absolute temperature, and just like in Charles' law, and P1 and P2, just like in Boyle's law, refers to absolute pressure. So we have to do two conversions here. That's one thing we want to keep in mind. So a 300 cubic inch sealed air tank is sitting outside in the morning, and the temperature inside the tank is 62 degrees Fahrenheit. The pressure gauge reads 120. That's not the absolute pressure, that's the pressure gauge. And by afternoon, the temperature inside the tank is expected to be close to 90 degrees Fahrenheit. What will the absolute pressure be at that point? Well, let's think about that too. So if I increase the temperature, right, it's likely we're going to have to increase the pressure here as well. So here we go. Volume is 300 cubic inches. Pressure 1 is 120 pounds per square inch. And of course, that's the gauge pressure. And T1 and T2 are both 62 degrees and 90 degrees Fahrenheit respectively. So we have to do some conversions. Let's convert our pressure first by adding 14.7. That gives us our atmospheric pressure in P1. And now let's convert our temperatures into Rankine. And so now we have our T1 and T2 being 522 and 550 respectively. And let's go ahead and look at our formula as far as P1, T1, P2, T2, plugging these things in. Okay, we would just multiply by 550 on both sides, right? Because that's all we need to do to solve for P2, or you can cross multiply and divide. It's up to you. It's just a proportion. And so we get P2 equals roughly 140 pounds per square inch. That is the pressure, and that would be the absolute pressure, right? If you wanted to find the gauge pressure, what would you have to do? You would have to, well, instead of adding 14.7, you would be subtracting 14.7. And we can do that on all the rest of the problems too. I may ask you questions about finding out what the absolute pressure might be, or what would the gauge pressure be. And you're going to have to add or subtract at the, you might have to subtract that at the end. So again, the absolute pressure would be 141.9. And if we go back, like I said, the original pressure, right, was reading at 120, but we added, it was 134.7. And now it's going to read, as we said, 141. So the pressure did increase as the temperature increased, maybe not as much as you may have expected, but it did increase, right? So again, if the absolute pressure, as I was saying, is 141.9, what is the pressure reading at the gauge? The gauge pressure would be reading 127.2, right? And again, that would be more of a gauge pressure. But notice that it wasn't just 14.7 more, right? So keep that in mind as far as the original gauge, okay? Or if you would have solved for what it was, in terms of not doing the conversions first. So the trick on these problems is making sure that you do the conversions that they need to be, put them in the units that they should be in the formula, and then you can always convert them back if you need to. Okay. And so that's what we're getting, right? What is the pressure reading at the gauge? It would have been 141 point, they're just rounding. All right, so just some things within a pneumatic system. You're going to go ahead and watch a video on this anyways, which really helps to identify the components. We have the receiver tank, which stores the air. You have the transmission lines, which you've seen before. We just use the little tubing, and we'll be using black tubing for our pneumatics. There's the compressor. We'll talk about you'll see a video that talks about what the compressor does. There's actually several different types of compressors, which basically just brings air into the reservoir tank, and as it keeps pumping air in, right, the pressure increases. And then you have some cylinders over here. More or less, we call those a pneumatic cylinder or an actuator. There's filters involved in a pneumatic system to keep air out, because air makes things rust. And then we have some regulators to make sure that the pressure stays constant or at whatever pressure that system needs. And finally, you have some drains as well. That would be to drain off any moisture that it's bringing in within the air. And there's some directional control valves, which usually we can start calling those solenoids. I believe that's what they're referring to in this photo. And essentially the solenoid is part of the control valve, which is an electromagnet switch that it basically lets air in different places within the cylinder. All right, and then you have your pressure relief valve. If too much pressure is trying to be pumped in, it can exit out there, which we have these as well in our systems. Okay, what possibilities may be on the horizon for pneumatic power? These are kind of cheesy. Could it be human transport? Actually, for those of you that are familiar with Tesla, Elon Musk, and the Hyperloop, this is not what the Hyperloop will look like, but more or less it depressurizes actually a tube, right? So that things don't have that, the pods won't have air resistance kind of driving through. But pneumatics that maybe you've seen before in the old school days, that made sense if it wasn't with pneumatic tooling. If you've ever been to a bank, that's how you kind of put the money in those little pods, and then they suck them up through the system to get it to the teller. That was all back in the day. But now we have more self-banking, where you can take pictures of checks and whatnot, and you can go deposit things and money even at ATMs. So maybe you haven't seen those things, but they're around. And that's it. So if you're confused by the questions, I'd go back and rewatch them once again and kind of file those down. Hopefully you took notes, and go ahead and now try some practice problems that relate to those ones that you just saw in the video. Thanks for watching.